heard them this morning, so I won't go over those again, but let me mark them present, like we did this morning. All right. Now, that's the thing. All right. So today's the 23rd still. Got it. Okay. We are now recording. Sorry, I didn't have the scroll mark before we started recording. So let me get somewhere I can see it.
Well, I guess with these, you just keep looking at numbers and you kind of see.
Okay, yeah, I didn't catch which one you were saying. Could you say it again? Page 5.
Was page
522. 57. All right. Okay. Let me set up the slideshow first. Current slide, and I'll do it on this slide as soon as it comes up. Okay. Here we go. All right. This is page 522. Whoops. Let me get my pen activated. Dark purple. Page 522, and this is 10.1 exercise. And here we go again. 10.1 exercise. Let me mark you here. Marcus is here. All right, still waiting for. Got the Y chromosomes, waiting for the X's. Okay. And 10.1, and you said 57? Right, 57. All right. What it says to do in these, use the appropriate limit laws and theorems to determine the limit of the sequence or show that it diverges, one or the other. Okay, so 57 is A sub n is equal to n sine pi over n. Okay. All right. All right. Now, one like this text, especially I think maybe all calculus texts, love these kinds of problems because, frankly, this has no limit. Okay? However, this value here stays between plus or minus 1. Always, right? Okay. Now, they didn't say use the squeeze theorem. That's what I would use because, but they're asking this before they got to the squeeze theorem. But what I would say, or at least for the moment here, and you know, if you look back on squeeze theorem, we have covered it before I assigned the homework, but it's you know, I think it's still somewhat legal to use. Wait, okay, wait. No, okay, sorry about that. 1 over n, that would have been fine. This one, determine the limit of the sequence or show that it diverges. I'm sorry, I was thinking 1 over n times sine pi over n. That would be okay. This one, no. and we don't even need squeeze theorem to do that. 1 over n would need squeeze theorem, but this is just n. Well, I think you could follow the same type of thing I just said. This is always okay. They sort of give you a hint. Use the appropriate limit laws and theorems to determine the limit of the sequence or show that it diverges. So the limit law you would use, of course, would be basically the product one. That would be, this would be you're not really, you are doing, if you do the limit as n approaches infinity, and do the limit here as n approaches infinity, this would then be the limit as n approaches infinity of n times the limit as n approaches infinity of sine pi over n. Now, it seems a little silly to go through all this, but I think it's legal to do. Because that's the only kind of hint they told you. Use appropriate limit laws and theorems that are saying that too. So I guess we could have used a squeeze theorem if we needed to, but I think this will do it for us. Okay. Basically what I said before, if you think about it, this thing is undefined, pi over n. Okay? It gets, as n goes to infinity, that's becoming a smaller and smaller number. And then taking the sign of a smaller and smaller number, and n's going to infinity, so these are all positive values. Basically, it stays between plus and minus 1, right? So sign's always between that. The smaller and smaller number just stays. So that has no limit at all. Okay? This one, the limit as n goes to infinity of n is going to infinity. That has no limit. And since this one's definitely not going to 0, there's no way you can control that either. So this is going to be, so I think that's all you have to do is sort of talk your way through that. That limit doesn't exist, right? Is that in the back?
Maybe I looked at the wrong answer. I thought that it was pi. I thought it was divergence.
It's divergent, yeah. The limit doesn't exist. It diverges. That means the same thing. And that's what it has in the back. Diverges.
Mine has pi on it.
Is what?
Mine says pi.
Pi. I've got to, I think something might be screwy there. Let's see, 10.1. And this is 57. Limit as n approaches infinity of n times the sine of pi over n. Okay. There's one way, perhaps, to fiddle with that. Well, let's try it. I don't see what's wrong with this reasoning, but let's try one other thing. Let's come up with a new variable. What you want to use? Say again? X? Everybody's favorite, right? Let's let x equal 1 over n. You okay with that? I think of x as a continuous variable in, well, I think we're okay with that, okay? Then what we have here is the limit, and basically as n goes to infinity, then x will be going to 0. Would you buy that? Okay. So then we have the limit as x is approaching 0 of, and if x is 1 over n, n is 1 over x, right? Okay. Lost the screen. So this would be the limit as, let's just leave it here, use this one. That's okay, still going from here to here. This would be this then. This would be 1 over x, right, times the sine of x pi. Wouldn't that be true? Pi x. I like pi x better, but it's okay. Now, if you remember back from Cal 1, or somewhere back in the long time passing, that the limit of, as x approaches 0, of sine x over x was 1. Do you remember that? Okay. That's true. Okay. Now, I still can't for the life of me see how they got pi out of that. That was the closest way I could figure to either. But I still don't see how pi comes out of that one. Unless you did another trick. Let y equal, this may work, x pi, then I'm afraid this may work. Okay, I can't swear to it now. This is a bit absurd, but let me write it down. X is equal to y over pi. Okay, let's plug that in and see what we get. And of course, as y goes to infinity, x goes to infinity, y is going to, x going to 0, y is going to 0. So this then would be the limit as y approaches 0 of, and 1 over x is equal to pi over y. Yep, unfortunately this is going to work, okay? Never would have guessed this, okay? So 1 over x is pi over y times the sine of y, because y is equal to x pi, right? See it? And this is now the limit as y approaches infinity of pi times sine of y over y, which we just showed. Then the limit law says this is pi times the limit as y approaching zero of sine y over y, and that is 1. So it's pi times 1 is pi. They were right. That is how it is. Now that is doing a bunch of stuff that we haven't really done yet, but those are all legal steps. Do you see how that came about?
Right there where you put limit, sine y, so you don't have to substitute.
Say again.
Right there on sine y.
This one?
No, here before.
Huh?
It's like the step right there.
That.
How do you so instead of you don't have to substitute it into the sine.
Don't have to what?
You don't have to substitute in.
Yeah, okay. Here's what I was using before. We already did this one and got here, right? Okay, here's my next substitution. Let y equal pi x. I wish I had written it that way. Then I could have just done this. Then divide both sides by x and both sides by y. You get 1 over x is equal to pi over y. This. Okay? Now, plug that in here. 1 over x is pi over y times the sine of pi x, or x pi, is y. Okay. See that? Okay. Then get the y's together and pi on the outside. Pull it all the way outside the limit, because you can do that. It's just a constant. And the limit of sine y over y is 1. As y goes to 0. I don't know if you remember how that looked, but I don't know if this is helpful or not. This is the identity function, and this is your sine function. Okay, that's pretty ugly drawing, but generally it doesn't come down to quite that. For this region in here, as x is approaching 0, they're the same values almost on top of each other. And when you actually plot this, you get at 1, of course you can't divide by y, divide by 0, but everything else does like this. You know, it's that kind of function. So it is approaching 1 as x approaches 0 from the left or from the right. And the reason is these are almost the same function. As x approaches 0, they're almost on top of each other. Of course, you get a little bit further away, sine is less than this, and sine is less than that. So the ratio is of sine y over this is a little bit less than 1. Right there near 0, it's coming close to 1 with a hole in the function there. But that limit does exist because it's the same as the left and the right. So they're right. It is pi. The limit laws, as we understood, that would have screamed at me that was going to infinity and that was staying between plus or minus 1, and just going crazy between that. And I said, still going to infinity. No, it isn't. That's gracious. I would not have guessed that. It doesn't look like it makes sense. But I guess what you could do is just start plugging in some n's and let them get bigger and bigger and bigger and see what happens. And supposedly that should be getting closer to pi. That's not how they said to do it. They said using the limit laws. But it's, sure enough, using a couple of well-placed substitutions and the limit laws, yeah, that works for you. Good question. I hadn't done that one before. And that's how you go about doing it. Wow. Was that the only one or the others?
No, I haven't.
Okay. All right. Good deal. Glad you had done that one. Brought something out. All right. All right, to erase the board here. Okay. So what we're doing next, we've done example 9, the paragraph under example 9, under that little red square after 9. As another application of the squeeze theorem, let's consider this sequence. A sub n is equal to 5 to the n divided by n factorial. Okay? Now, they want you to use the squeeze theorem on this. Okay? And I think it's beneficial to start looking at some of the values first before you start trying to apply the squeeze theorem. Okay? And here's what I mean by that. Let's do a sub 1. We could do a sub 0. Does anyone know what n 0 to factorial is? It's 1. That's just a definition. So a0 would be 1 over 1, which is 1. Okay? A sub 1 would be what? A sub 1 would be 5 over 1, because 1 factorial is 1. So that would be 5. A sub 2 would be, anyone know? 2, which would be 11.5, right? No, 12.5. Well, divide. Okay. 12.5. A sub 3 would be 125 over, you know what 3 factorial is? 6. 3 times 2 times 1, blah, blah, blah. So this would be 20, blah, blah. 20.833 or something like that. Okay? A sub 4, what would that be? Is that 625, isn't it? All right. We're getting there. Faith is here. We still got the silver to come. Did she tell me last time she was going to be out today? Yeah. She did. I thought so. Okay. The old gray cells ain't what they used to be. Okay. 625, I think. That's 5 to the 4th power. 25 times 25, I think, is 625. Got it? And then divided by 4 factorial, which would then be 4 times 6 is 24. And if you do that, I think you get something like 20.83 again, don't you? Huh? 26.041. Okay, we'll take that. Okay. A sub 5 would then be multiply 625 by 5 or do 5 to the 5th power, whatever you want to do. It's a huge number. What is it? 15625. Yeah, I'll buy that. Divided by 120, I believe it is. And that another 26.04, something like that. Yeah. Oh, we're doing the, it's not really an example, it's underneath example 9, very bottom of the page, page 517. 10. 10.1. Yeah.
That's 130.2.
Okay. I think we did something wrong. Let's do 5 to the 5th power again. Because that went up way too fast, I thought. Okay, wait one. Say that again. Okay, all right. 3125. Is that what you said? Okay. Then divide that by 120.
26.04.
Ha! 26.04, blah, 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 just like before, right? A sub 6 would be 5 times that in the numerator. I think that's your 15, whatever you gave me, right? What was it?
15625.
625. And divide that by 6 times that would be 720, right? And I bet you that's around 20.83 or something. Maybe not exact, close though, isn't it? Yeah, 21.7 something another. Okay. So you see it's coming down now. Okay. Now, so they say application of the squeeze theorem. And by the way, they did a few of these in the book, but they skipped a bunch. And after a while, even though both the numerator and the denominator are going up without bound, in fact, they're going up pretty dramatically, who's winning? Well, what you have to do is, it looks like right around n equal 5 from there on, and this really isn't the squeeze theorem, but it really is the better way to do this problem. After a equal 5, then so for n greater than 5, a sub n plus 1 over a sub n. That's the thing that's of interest here, okay? Well, what that would be, in other words, your numbers are getting small, and how are they getting small? What would a sub n plus 1 that be? That'd be 5 to the n plus 1 over n plus 1 factorial, okay? And divide that by 5 to the n over n factorial, right? That's what a sub n would be, right? Now, if you look at that ratio, I'm going to invert and multiply. That would be 5, not quite, 5 times 5 to the n. That's 5 to the n plus 1, right? You know, 5 raised to the nth power, and then the next 5 to the n plus 1 be 5 times 5 to the nth, right? Okay. Divided by, and n plus 1 factorial is n plus 1 times n factorial, right? Say, give me an n, any old big n. 8. That n factorial, 8 factorial would be 8 times 7 times 6 times 5 times 4. 7 factorial is 7 times 6 times 5 times 4. So 8 factorial is 8 times 7 factorial, right? Okay? So that's your numerator. The denominator, I'm going to put invert and multiply n factorial over 5 to the n. These go out, right? These go out, and you have 5 over n plus 1. Okay? Well, for any number greater than 5, this is a number less than 1. And then let n go to infinity, and that's going to be 5 over 1,000,001, or something like that. That's getting closer and closer to 0. Now, that's the way I would approach this, and that's why out here, as n gets bigger and bigger and bigger, you're closer and closer to zero. Because you're not adding anything else. In fact, these are going down and going down pretty quickly. They're going down almost like this went up, but then down here they're just closer and closer to zero. Because everyone is, the next one is going to be a number less than 1. So from this point on, this one is 5/6 of that. This is 6/7 of that. That's 7/8. I'm sorry, I said that. This is 5/6 of that one. This would be 5/7 of that one, 5/8 of that one, 5/9 of that one, 5/10 of that one, 5/11 of that one, 5/12. And soon you're getting down to smaller and smaller and smaller. Number is going to zero. Now, squeeze theorem, I guess you could use, but why? I mean, they show the table, they show the graph, but they don't really show how you use the squeeze theorem, okay? But they do this one, and it's very similar to it. And there is the table, and you see that is going to zero. So they're not using the squeeze theorem. They're just showing it to you. But here's what we just did, okay? They say it suggests that a sub n increases initially, then tends to zero. The next example, and that's what they're going to show, we verify that a sub n, so this is a slightly different problem, though it certainly would fit, is equal to r to the n over n factorial. That's just with r equal 5. That's the one we were looking at. This is with r equal any number in the world. Okay? It converges to 0 for all real numbers r. Let's just correct that. Positive real numbers r. It does for the negatives too, but that gets to be such a mess to try to do. So let's just leave it positive. Okay? And then they'll talk about this in Taylor Series 10.7. We're not going to go there. So anyway, this is example 10. Prove that the limit of this, as n approaches infinity, a to n is limit as n approaches infinity, r to the n over n factorial, is equal to 0 for all r. Let's assume first r is greater than 0. Okay, we'll do that. Okay, if r is equal to 0, it's sort of a meaningless problem. It's got to be 0. Okay, and then I think someplace down the road they'll do r less than 0, but I'm not even sure they do that. Let me see. Yeah. And that goes back to example 8, which shows that the limit of the absolute value, if the limit of absolute value of something is equal to 0, then the limit without the absolute value also has to be 0. Okay? And it sort of, you can use that and then not. So let's just do r greater than 0 for now. So let's start for r greater than 0 to start with. All right. Now, remember the squeeze theorem. Here's what it says. Let three sequences you have, a sub n, b sub n, and c sub n. B sequence sets for some number, capital M, then you can order these. That b to the n, b sub n is less than or equal to a sub n is less than or equal to c sub n for all n greater than m. Okay? And then if you can show that the windows, the pieces of bread on your sandwich, the b sub n and the c sub n are both going to L, then the meat in between has to be going to L too. Okay? That's what we're trying to show. So here's what they're going to do. they first need to pick the m for some n greater than m. Well, what m will you use? Okay, let m be some number that's less than or equal to r, and r is also less than or equal to m plus 1. So in other words, whatever your r is, the last one was 5. So pick m's 5 would do fine, and the next one up would be 6. Okay? Or m equal, yeah, that would work fine. And if r were a number like pi, then use m3 and m plus 1 would be 4. That would work. Okay. So r can be any real number. Because it says for all r, it doesn't have to be an integer. All right. Now, as long as you take, and this is what squeeze theorem says, as long as you take n greater than the m, okay, for any n greater than m, you can rewrite your r to the n over n factorial as a product of n factors. And this is basically what we did before, and here's what they're doing. This is what your target is here then. Okay? And we sort of did this. Okay? The first factor, now remember, m is something just below or equal to r. So the r sub m would be, and this would be m factorial, so this would be m times m minus 1 times m minus 1 times 2 minus m. So 1 times 2 times 3 times 4 times up to m. And for every one of those, you have an r, the r, and r, because it's r to the m, right? So you have m r's and m denominators here from 1 to m, right? Okay. That's r to the m. Okay? Now, beyond that, for all the values beyond that, you got r over m plus 1, plus r over m plus 2, plus r over all the way up to n, because you're taking the n greater than this m. Okay? So, however far you need to go. This is some constant factor, whatever it is. Maybe a huge, well, it's not going to be that big, but it's going to be some number. And then every one of these, because the m plus 1 is greater than r, every one of these is a fraction that's less than 1. Every one of them. This is less than 1. That's certainly less than 1. Same r, but bigger denominator. Same r, but an even bigger denominator until you get up to n. So every one of these, and these are factors, are multiplying a number less than 1 by another less than 1 by another less than 1. They're all getting smaller and smaller. After a while, you get a number that is considerably less than 1. Okay? And because specifically all these are less than 1, then this last one here, you multiplied it by something less than 1. So this number c times r over n, this last factor here, because all these factors in between were less than 1, this thing has to be less than that thing. Okay? And you basically almost got your squeeze theorem in place now. As n goes to infinity, which is what's happening here, that's going to 0. Always, no matter how big. Just get past this m greater than r, past that, and this thing's going to 0. Now, before that, it wasn't, but past it, it definitely is. Because r is some fixed number, n can go to infinity. So at some point, you're going to pass this, and this is now a geometric sequence, which your denominator greater than the numerator, that's going to converge to the numbers. Well, it's going to go to 0, basically. All right. Okay. And then they use example 8 to show what happens if you have R actually negative, and it works too. Just do the same thing for absolute value that we did here, and then for the absolute value one, and then this is always less than that. All right, theorem 4. Okay. If f of x is a continuous function, just any old continuous function, it doesn't have to be smooth, just continuous. And the limit, as n goes to infinity, of a sub n is equal to some, it's L. It's not infinite. It's not increasing without bound. It's not fluctuating. It's some fixed value, L. Then the limit as n approaches infinity of f of a sub n, which now we're taking a function of a sub n, but you're letting n go to infinity, so a sub n is going to a sub l. This is going to be, now here is the shorthand for what we're saying here in this theorem. The limit of a function of an infinite series is the function of the limit of the infinite series. That's basically what theorem 4 is saying. So bring the function on the outside, that'd be the limit as n approaches infinity of a sub n, but we know that's L, so this is going to be f of L. That's it. Okay. In other words, bring the limit inside a continuous function. Okay? Or take the function outside the limit, whichever way you want to look at it. Swap the roles of the limit and the function. Okay? And if you already know what the limit of a sub n is, L, that was given, then that's just f of L, whatever that happens to be. So let's apply that in exercise example 11. And I'm pretty sure that 11 isn't given, so let's do it here. Here is a sequence. A sub n is equal to 3n over n plus 1. Okay? So it says apply theorem 4 to this sequence and to the function. And the first of these functions is going to be f of x is equal to e to the x. All right. Well, got a little bit of work to do here. Okay. First, we need to figure out what the limit as n goes to infinity of a sub n is, which would be the limit as n goes to infinity of 3n over n plus 1. Now, remember my suggested technique for taking a limit as n is going to infinity when you have n in a numerator and denominator. Second? Divide by n, numerator and denominator, and this would be the same as the limit, still as n is going to infinity, of 3, because that's 3n over n, over 1, that's n over n, plus 1 over n. Okay? In other words, we multiplied this by 1 over n and multiply this by 1 over n. Okay? Numerator and denominator. This, the n's go out, and here you have n over n plus 1 over n. N over n is 1. So that's what that is. Well, what does that equal when n is going to infinity? 3, because 1 over n is going to 0. So this will be 3. All right? So, apply this to this one. alpha of x is equal to e to the x, okay? So we're doing f of a sub n and taking the limit as n goes to infinity, and this would be the same as doing f of that limit a sub n, which we just did, and that was going to be 3, so it's alpha of 3, and what's alpha of 3? Alpha of x is equal to e to the x. Alpha of 3 would be e cubed. Okay? That's it. That's really all you have to do. Okay? And the b part is doing f of x equal to g of x equal to x squared. Okay? Well, then what we're doing is the limit as n approaches to infinity of g of a sub n, which would be g of the limit as n approaches infinity of a sub n, which we just did. That's 3. So it's g of 3, which would be 9. 3 squared equals 9. Okay. The theorem may be a little on the fuzzy side, but the application is pretty straightforward. I mean, it's just about as easy as anything we are going to do in the course, I want to say. Okay. Now, remember a lot of what we're concerned with infinite series. Are there any questions about any of this? Okay. About infinite series are these. Okay. Does it converge or not? Does it diverge or not? Can we tell? Okay, those kind of questions. Well, the next theorem is going to help us with some of that, hopefully. And that's the bounded sequences. Okay, now this is not a theorem, sorry. It's just a definition. Bounded sequences. Okay. Some sequence a sub n is bounded from above if there's some number m up here, such that the a sub n is always less than or equal to that number m for all n's you get to. That number is called an upper bound. So say you have some sequence here, and it's doing all sorts of weird things. But if you know, guarantee that value, every one of those dots is always going to be less than, better on this nice wide thing, always going to be less than or equal to some value m. That every one of these varying dots, none of them go beyond m. They always stay below m. If you're m high enough, they never, no matter how far out there you get, never get above m. Then m is called an upper bound. Now, you can have huge upper bounds that they don't even come close to, or come closer and closer until you have the least upper bound. That one we're probably a little more interested in, but we'll get back to that. Now, they're bounded from below if there is some number little m, okay, big M for above, little m from below, such that your sequence a sub n, that nth term there, is always greater than or equal to m for all n's. So if this was your thing here, and they're going all over the place, pick some m down here that they're always greater than or equal to. Okay? Then that's called a lower bound. Now the sequence a sub n is called bounded if it's bounded both from above and below. Now a sequence that is not bounded is called an unbounded sequence set. In other words, you can't ever get a capital M and a little m that bracket it. Either it's going to dip below the lower one or go above the higher one. No matter how far you go, you can't get one big enough or small enough. Okay? that would be an unbounded sequence. Does that make sense? Just a definition so far. All right. Here is a pictorial illustration of that. I was throwing around. Everything, if this is your sequence, and they never get above this value here, every M up here, capital M, would be upper bounds. Your least upper bound appears, at least at this point, to be that value right there. Okay? Because all your values are less than or equal to that M. And if this is indeed your sequence, then your lower bound could be any value here. Now, they could be negative, they could go on and on and on, but the least, or the greatest lower bound would be that, at least if nothing weird goes on out there. Okay? Sorry, I should have blown this up. Okay? Got the concept here. Now, they put a little thing here. A convergent sequence is bounded, meaning it has an upper bound and a lower bound, and it never goes outside those. Okay? Then this is now. Notice what it's not saying, though. It's not saying a bounded sequence converges. It just says a convergent series is always bounded. Always bounded. You can't put the reverse on it. It's not an if and only if. It's only goes one way. Convergent series has to be bounded both from above and below. Okay? Has to be. Okay? And that actually is the next theorem. Okay? Convergent sequences are bounded. Okay. If A sub n converges, then A sub n, by definition, if it converges, is bounded, above and below. I mean, that makes perfect sense if you think about it. If it's going to converge to something, that means there's some limit out there that it's going to reach. It's got to be bounded. Find something above the greatest and below the least, it's bounded. Okay? If that series converges, it is bounded by definition. Okay. Now they go through a little proof of that as well. And let's see if they do any of the proof here. Not quite. This is going into the next thing. But I mean, I hope that just thinking about it, arm waving, you can almost see it has to be true. And when you read through the proof, you'll see it basically is quantifying the arm waving, pretty much. Okay? Putting variables on. But let's look at another sequence here. Here's a sequence. And this is an increasing sequence. Okay? A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, A sub 6, A sub 7, A sub 8, A sub 9. Okay. Now, an increasing sequence, that's an increasing sequence. Every A sub, A sub P is always greater than A sub P minus 1, the previous in the sequence. It may not be by much, but it's always greater than, okay? I guess you could say or equal to, but specifically greater than, okay? That's an increasing sequence. But if that increasing sequence has an upper bound, then it's got to be approaching a limit. Now that limit may be the upper bound or maybe some number less, but it's going to have to be approaching it. Now, we looked at several of these already. Let me just make up one. You could come up with the representative. 1 over 2, comma, 2 over 3, comma, 3 over 4, comma, 4 over 5, comma, 5 over 6, comma, 6 over 7, comma, 7 over 8. What's that? Is that increasing? Yeah. 1/2, 2/3, 3/4, 4/5, 5/6. Yeah. It's increasing. Is it bounded? Think about it. 1 million over 1 million and 1. Okay? It can't get greater than, it can't even reach 1. Okay? Yeah, it's going closer and closer to 1. It's an increasing sequence with an upper bound of 1, and that happens to be its limit. You can say its upper bound was 2, but its limit would be 1. Okay? 1.1 would be an upper bound, but the limit is 1. It's getting closer and closer to 1, but never gets there. So that's its limit of 1. Okay? Now, another name for this, an increasing sequence, would be in this case, a monotonic sequence, meaning it's only going in one direction. It doesn't go here, come back, go here, come back. It's not 2 steps forward, 1 back, 2 steps forward, 1 back. It's not that. It's always going forward. The steps may be getting infinitely small, but it is always moving in the same direction. So that's another name for it, monotonic. Now, if it's a decreasing sequence, then that would be monotonic as well. It would just be in a negative direction. Okay. So they also mention here, I jumped ahead too far, there are 2 ways that a sequence can diverge, and we've already seen this as well. One is exploding. It's getting infinitely large positive or infinitely large negative. It's not bounded, okay? Those sequences are diverging, for sure. But there's another way, and we've seen this one too. It may stay between 2 values, but never settle down. Cosine, sine, it stays between plus or minus 1, but it varies anywhere between that and never converges to anything. So there's the other kind. They have a name for that. 2 ways a sequence can diverge. One is being unbounded. The other, it bounces back and forth between 2 limits, but never settles down to, between 2 values, but never settles down. So that's all they say. They didn't have a better word for it at all. Settles down is their word for it. Okay. Now, obviously, a monotonic sequence, monotonically increasing, could diverge if it has no limit, but if it's monotonic and has an upper bound, then it's got to converge to a limit. Okay? If it's monotonic and decreasing, monotonic, not tonic, I said it in the monotonic and decreasing without bound, then it's diverging. But if it's decreasing with a bound, then it also has a limit. These are just go back and forth and back and forth. They're not monotonic. And if they never approach a limit, positive or negative or in either direction, then those are also diverging sequences. I think that leads to no. Well, they're a little out of order here. Okay? Let's get the theorem first, then we'll come back to that table. All right. And this is sort of theorem 6, kind of says what I just did. If you have a bounded monotonic sequence, they're always going to converge. Whether it's monotonically increasing, if it's bounded from above and below, of course, too, then it's got to converge to some limit less than that m, capital M, or greater than the little m. So if a sub n is increasing, monotonically increasing, and a sub n is less than or equal to m, so you have some bound there, then a sub n converges, and the limit is also less than or equal to m. It may be m, but it's definitely going to be less than or equal to if it's bounded by that m. If a sub n is a decreasing function, and let's call it a monotonically decreasing function, meaning it's getting every term is less than the previous term. But a sub n, that nth term, whichever it is always greater than or equal to some lower bound, then a sub n converges, and it converges to some value greater than or equal to that lower bound. It's got to. It's decreasing, but it's never reaching that m. It's going to have a limit greater than or equal to that m. Okay. Now I think we can do example 12. And I think this table refers to example 12. All right. Verify this. A sub n, this is a sequence, a sub n, is equal to the square root of n plus 1 minus the square root of n. I can't write. Okay. Verify that that is decreasing and bounded below, and then the question is, does the limit of that exist? They don't ask you what it is, they just say, does it exist? So we've got to verify two things. First, that it is a decreasing function, and secondly, that it's bounded from below. Okay? Now, how to verify that it's a decreasing function? Well, one way they did, maybe not the very best of ways, certainly maybe not the fastest way, but certainly is one, is just pick some values for n. Okay? Now, you could have started with n equals 0, and you have done, this would be square root of 1 minus the square root of 0 would be 1. So a sub 0 would have been 1. A sub 1 would be the square root of 2 minus the square root of 1. That's 0.41, blah, blah, blah. Square root of 3 minus the square root of 2 is, do it out and see, and you'll see. Keep doing that, and it's getting less and less and less. Now, obviously, it's never 0, right? The square root of a bigger number is going to be greater than the square root of a smaller number. So it's bounded from below by 0, for certain. Now, there may be a greater lower bound, but definitely that. So it's a decreasing function, monotonically decreasing function, and it's bounded from below, guaranteed that it does have a limit. We haven't figured out what it is yet. It could be 0 or it could be something greater than 0. We haven't seen that yet. Now, is there any way to tell for sure? Let's try our old technique of dividing. Now, this isn't a ratio, so you can't divide by n. That wouldn't be fair. Okay? You got to divide something same in numerator and denominator. Now, the table indicates it looks like it's decreasing. But how can we say for sure it is? Well, remember we could represent that sequence as a function. And that function be f of x equal to the square root of x. And all we have to do with that is show that f prime is negative. And if f prime is negative, that means the f values are getting less, right? That would be true no matter what value you put in there. So if I'm going to take a derivative, I don't like to write it in the square root. I like to use exponential notation. What would that be? X to the 1/2. So what we have to do now is figure out what x prime is, f prime is. What would that be? One half minus 3/2, right? No, wait, minus 1/2, I'm sorry. I was doing the next derivative, okay? Minus 1/2. Because you subtract 1 from it, okay? Now,
Why did you change,
what's that?
why did you change base of n to fx, but why is it equal to,
Wait, I don't have this right because what we have, I'm sorry, you do this, except here's where I messed up. What I need to do is f of x is equal to the function, I'm sorry, which is the square root of x plus 1 minus the square root of x. It's the whole function. And this is what I want to write. And let me just get rid of this altogether. Now let's do my f prime. Okay. I want to write this as x plus 1 to the 1/2 minus x to the 1/2. That's what I should have been doing. Okay. Now what would that be? Just like we did before. 1/2 x plus 1 to the minus 1/2 minus 1/2 x to the minus 1/2. Okay. Now, that would be 1/2 times 1 over the square root of x plus 1 minus 1 over the square root of x. That's still there's still something wrong here. Okay. Yeah, no, that's right. Okay. Because pick any x, 5. This will be 1 over square root of 6 minus the 1 over square root of 5, right? Well, if you have a larger denominator here, all numerators are 1, then this number is less than that number. If your value is positive, 6, okay, square root of 6, okay, is a positive value, and square root of 6 is greater than square root of 5, but 1 over square root of 6 is going to be less than 1 over square root of 5, obviously, right? Because bigger denominator means a smaller fraction. Larger denominator, smaller fraction. Smaller denominator, larger fraction. So this thing is always greater, less than, goodness gracious, I got my sign backward. Okay, is less than 1, less than 0. Okay, because that difference, the larger number is subtracted from the smaller number. Okay, so this part is less than or equal to 0. So meaning it's negative, so the whole thing is less than or equal to negative 1/2. Okay, they didn't go so far as to say that, but it is. Okay, now, so you've shown number 1 is decreasing. It's bounded from below. We knew that because it's 0. It's never as little as 0. Okay. Yeah, m equals 0, always bounded by that. Theorem 6 then guarantees that it does have a limit. And it says that limit does exist and the limit is greater than or equal to 0, in fact, we can show that L is equal to 0 by noting that f of x can be written as, and they do another little thing here. If there's your f of x, is that, here's a trick. F of x is equal to the square root of x plus 1 minus the square root of x. We already determined that, right? Now here's the trick. Remember how we used to rationalize denominators? What we're going to do now is rationalize the numerator. Let's multiply this numerator, and this is over 1, by the square root of x plus 1 plus the square root of x. Multiply by the conjugate. But then you're going to have to multiply this by the conjugate. X plus 1 plus the square root of x, right? Multiply the numerator by that, you got to multiply the number. So what does our numerator become now? FOIL it. What does that give you? Square root of x plus 1 times square root of x plus 1. X plus 1. Now, the cross terms, if you went to FOIL, you have minus plus this minus this. That adds a 0, right? So you wind up with just minus x, right? Minus x. Well, guess what? That's just 1 over the square root of x plus 1 plus the square root of x. Okay? Now, what does that tell you? This is your f of x. Can be written in that form. And if you go backwards then and rewrite that as your a sub n, because this f of x was your a sub n, so go back and do that, that would be a sub n would then be 1 over the square root of x plus 1 plus the square root of x. I mean n. These are n, sorry. Okay. Those are both n's. N plus 1 square root of n. All right. What's the limit of that? Is n going to infinity? This gets big without bound. That gets big without bound. Add them together, they get big without bound. So that's going to 0. So the limit of that, as n goes to infinity, this is going to 0. Okay. So the limit does exist, and we actually can figure out what it is. 0. All right. Now, did we have to go to else? We could have seen this limit if we had just dealt with that and done the same thing we did down here. But what we couldn't show is that it's monotonically decreasing until we do go to else, do your derivatives, and show that's always negative. That's how we show it's monotonically decreasing. Okay. The table just indicates it. This shows it. Okay. Now, they do example 13. Yeah, this is the table for 13. Let's do this. Show that the following sequence is bounded and increasing. Here's the sequence. A sub 1, that's where we're going to start, is the square root of 2. A sub 2 is the square root of 2 times the square root of 2. A sub 3 is the square root of 2 times the square root of 2 times the square root of 2. Yeah. Dot, dot, dot. Okay. Now, says show that the following sequence is bounded and increasing. Okay. Now, frankly, I think the increasing part is probably going to be a little bit easier. Okay? And here's why. Let's start with the square root of 2. That's the square root of the number 2. And that, of course, is a number greater than 1, right? 1.4, 1.4. So, this one is 2 times that number greater than 1, right? And that's certainly then going to be greater than 2. 2 times a number greater than 1 is going to be a number greater than 2. And the square root of a number greater than 2 is going to be greater than the square root of 2. And just keep doing it, and every time you're taking the square root of something that's larger than what you took the square root of before. Okay? So, it's an increasing function. Okay? Second part was easier than the first. Okay? The first part says, show that it's bounded. Okay. Let's see. This is 2 to the first power. This would be 2 to the first power times 2 to the 1/2 power. Okay? That would be 2 to the 3/2 power. Right? Well, that's just showing it's increasing again. We've got to show that it's bounded as well. Okay? Let's find the number. Okay. The square root of 2 is, like we said, 1.4 approximately. And 2 times that is going to be something less than 2 times 2, right? Okay, because square root of 2 is less than 2, right? So 2 times the square root of 2 will be less than 4. So this is going to be less than the square root of 4. We've just shown that this is less than 2, because 2 times, no, this is less than 4, okay? The square root of 4, something less than 4 is going to be less than 2, and the square root of 2 times 2, yeah. So obviously, this is bounded by the number 2. Now, it may be something less than 2, but it's certainly bounded from above by 2. Because basically what you do is take the square root of this, multiply it by 2. Take the square root of that, multiply it by 2. Yeah. And just keep this square root of that gives you this one. Square root of that times 2 is something less than 4, but the square root of that is less than 2. So this is less than 2 times 2 would be something less than 4. The square root of something less than 4 is less than 2. So everything here is less than 2. Okay? So it's bounded from above by 2. It's an increasing function, but bounded by at least by 2. Okay? So the following sequence is bounded, and it's increasing. Now, prove the L. Here's what we're to prove. We've shown it's bounded, for instance, by 2. Okay? And we've also shown it's increasing monotonically. So if it's bounded and increasing by theorem, what was it, 6? No, too many pages. Yeah, by theorem 6, it has to have a limit. It says, prove that the limit L, which is the limit as n approaches infinity, of a sub n, these are your a sub n's, exist. We just showed it. It's bounded and it's increasing. The limit exists. But then it says compute its value. Okay. All right. Now how do we show? Okay, we've shown it's bounded and we've shown that it's increasing. Okay. Now, here's the thing that's helpful, if you want to do a table like that, okay, the square root of 2 is 1.4142. The square root of, okay, multiply that number by 2 and take the square root again. Okay? Multiply that number by 2 and take the square root again. Multiply that by 2 and take the square root. Multiply that by 2 and take the square root. Keep doing this. It's getting bigger all the time. It's an increasing function. We showed that. Okay? And it does appear that this number is getting, and we know that it's bounded by 2. We just showed that as well. And when you do this and show it is, there's not many numbers between 1.9946 and 2 that you could be converging to, so the limit must be 2. Okay? Now they do it a little more, they show this, and that sure indicates what you think it is. Here's how they actually show that. Okay? And this is basically a recursive sequence. Okay? Because a sub n is equal to the square root of, here's a sub 1, a sub 2 is the square root of 2 times a sub 1. Okay? So I'm going to make that n minus 1. I think you see that's going to be the case in every situation here. Okay? Now, if this limit does exist, and that's L, then the limit as n approaches infinity, we showed that it did exist, of this thing, is going to be the limit of this thing. Okay? Now, I might need to do it the other way. Let me see. Yeah, I think I need to do it the other way. Rather than doing n plus 1 here, do it this way. Sorry about that. Let me erase this. Okay. We were given this part. That's what L is. We also know that a to the n plus 1 is equal to, like we just said, the square root of 2 times a to n. Okay? Just doing it the other way. Pick an a sub n, wherever it is. Then the a to n minus 1 is going to be the square root of 2 times whatever that previous one. A sub 1, the square root of 2, a sub 2 was the square root of 2 times a sub 1. And the square root of 3 is the square root of 2 times a sub 2. So it is the square root of n plus 1 is that. Okay? Now, the limit, okay, sorry. Let's take a limit of both sides of this. The limit as n approaches infinity of this is equal to the limit as n approaches infinity of that. Okay? Now, what that is saying, if that is the limit of a sub n, it's also the limit of a sub n plus 1. I mean, it's the limit as n just keeps getting bigger. So this is L is equal to, the limit of this would then be the square root of 2L, because the limit of that is. Now that's a strange looking statement, but that is indeed true. L is equal to the square root of 2L. How could we solve that for L? How do you undo a square root? Square it. Square this, square that. So this is L squared is equal to, what's the square root of, the square root of 2L squared would be 2L. So this says that L squared minus 2L is equal to 0. That says L times L minus 2 is equal to 0, right? Well, either L is equal to 0, which we know is not true because L is positive. It can't be 0, okay? So the second one gives us L is equal to 2. That is your limit. And sure enough, that's what it indicates there. All right. Interesting little way to do that. All right, let's look at our preliminary questions. Let's see if there's anything else. No, there's not. So let's clear this out. Okay. Let's look at our preliminary question. Any questions on 10.1 before we do the preliminary? Let's do it. What is A4? What we're looking for is A4 for the sequence A sub n is equal to n squared minus n. Pretty straightforward. What would A4 be then? Yeah. It's what? Okay, wait. Oh, not this. This here at top. We're looking for A sub 4 if we're given that A sub n is equal to n squared minus n. If we can do it without a calculator, maybe. Second? 12, exactly. 16 minus 4 equals 12. Perfect. Okay? Number 2. This is preliminary questions 1, 2. Which of the following sequences converges to 0? N squared over n squared plus 1. B, this is A. B is 2 to the n. Or C is negative 1 over 2 to the n. Okay? And when it says converges to 0, that's assuming n is getting infinitely large. Second? C for sure. This one converges to, actually 1/2, isn't it? No, 1, you're right, 1. Divide both by n squared. N squared over n squared is 1, n squared over n squared is 1, 1 over n squared goes to 0, 1 over 1 is 1. You got it. This one? It diverges. It goes enormously large very quickly and never comes down. That one, however, is a factor that is multiplied, is less than 1, and it would be n equals 0 would be 1, n equals 1 would be negative 1/2, positive 1/4, negative 1/8, positive 1/8. Alternating signs and getting smaller, smaller, smaller. Converging to 0 for sure. Above and below. Okay. Next, number 3. And by the way, I don't want to say all. The preliminary questions in general, either all or odds are in the back. This one, they are. A sub 4 was 12, number 2 was C, and this, now we're doing number 3. Let A sub n be the nth decimal approximation to the square root of 2. Okay? That is, A sub 1 is equal to 1. A sub 2 is equal to 1.4. A sub 3 would be 1.41. Okay? And so on. Okay. What then is the limit as n approaches infinity of A sub n? Any ideas? Square root of 2, because everything is the next approximation to it. So the more you have, the more you've got there, and it's going to square root of 2. Sometimes it'll overshoot, sometimes undershoot. All these undershot. One did 1.4, 1.41, 1.414. But then at some point there, you're going to round up sometime or another. And anytime you do that, will overshoot it then. But you just keep zooming in on it closer and closer. So that is the square root of 2. And I think they got it too. They sure had better got it. Let me see. Oh, there it is. Yep, square root of 2. Okay. Number 4. Which of the following sequence is defined recursively? A sub n is equal to the square root of 4 plus n. Or B, this is A, B is B sub n is equal to the square root of 4 plus B sub n minus 1. Which of those is defined recursively, A or B? Recursively means it uses the previous value. B obviously does. A is just using n. So B is defined recursively. It depends on the previous value, and that's B. Good for them. Okay, number 5. I think I'm going to clear the screen. Is that okay? Theorem 5 says that every convergent sequence is bounded. Determine if the following statements are true or false, and if false, give a counterexample. Okay, 5a. This statement is, if A sub n is bounded, then it converges. True or false? False. You need to give me a counterexample. What's that? Okay, no, okay, that is true. But give an example of a bounded sequence that doesn't converge. Of n, yeah, both of those would be. They stay between plus or minus 1, but never converge. You're absolutely right. An even simpler one would be plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. It's bounded for sure, but it never converges, nowhere close. So both of those are quite good. Okay, B. If A sub n is not bounded, then it diverges. I can't write, but somewhere in there. Okay? If A sub n is not bounded, then it diverges. Huh? Yeah, that's going to be true. And because in order to converge, it has to be a bounded sequence. If it's not bounded, how can it possibly converge? Okay, that will be true. C. That means yes in Spanish, right? Okay, if A sub n diverges, then it is not bounded. That would be false also. Can you give a counterexample? Same as we did before. Plus 1 minus 1 or sine of n definitely diverges, never converges, but it's not. But it is bounded. Okay, same as before. So false, true, false, and they show the one you said for the first one, the one I said for the second one. So, yeah. So, got it. All right. Are we almost through? Oh, my. Or are we even past 3? Okay. Sorry about that. It was just too much fun to stop. Here's homework exercises. Do number 1. I've assigned some of these before. Any of the odds 3 through 11. Do number 13. Any of the odds 15 through 25. Either 27 or 29, or both if you choose. 31 or 33, or both if you choose. And then any of the odds 35 to 61, 63 or 65, or both. 67 or 69, or both. And then any of the odds 71 through 83. I'll let you choose as many or a few of those as you want. Okay? And I usually look at the further insights and challenges. If you want to look at them just to get a deeper understanding of something, you certainly can. But I look at them to see if I see any potential paper topics there. And they do talk about something called an arithmetic geometric mean. We talked about geometric mean, but we didn't talk about our arithmetic geometric mean. If you want to write on that, that might work. Or it almost seems like they're talking about harmonic. They're talking about harmonic number, which I think has to do with a harmonic series or something. That might be something if you can find enough on there. And then one other, Euler's constant. So you can write either on Euler, I think we've already mentioned him, or what the Euler's constant is, how is it used, where it's applied, whatever. So you can go for either of those. And we'll begin next time with 10-2. Okay. Here we go. This is mark my place. Begin with 10-2. Fantastic. We'll see you on Wednesday. We get to meet twice this week. Wow, what a change. This is the first Monday we've met together, right?